The topic of the video is Einstein coefficients and the relationship among those coefficients. If only two energy levels of an atom are considered, then we say that we are dealing with a two-level atom. If N1 is the number of atoms with electron in a lower level, and N2 is the number of atoms with the electron in upper level, um, in a sample of atoms which we consider as occupying a volume V, then the N2, which can be taken as the population of atoms with electron in the upper level, can be actually changing because of three processes. The first one is spontaneous emission of light, uh, and then the second one is stimulated emission of light, and then the third one is the absorption of light. Mr. Einstein has actually written that the rate of change of N2 due to the spontaneous emission as a negative A into N2, where A is called the Einstein's A coefficient. And he also have written the rate of change of N2 due to the stimulated emission as negative B sub 21 into rho, which could be function of frequency of light, into N2, where this B21 is called Einstein's B coefficient for stimulated emission, and then rho nu is called the spectral energy density of black body radiation. And so here we assume that we have a black body which is in equilibrium with the sample of atoms that we are considering. And for the case of uh, the rate of change of N2 because of absorption of light between the energy levels E1 and E2 as B21 into rho nu into N1. So he considered that the rate of change of N2 is because of this factor. And here B21 is called Einstein's B coefficient for absorption of light, and then rho nu is the same thing that we have taken as the spectral energy density of a black body. So we kind of have this energy level diagram for the two level atom. With energy E1 it will be N1 population, and with energy E2 it would be N2 population. So the total effective dN2 by dt, I mean the effective change of N2 as function of time can be written as it is due to the spontaneous emission and then the stimulated emission and because of absorption. And as the N2 population increases, that's the reason why we have taken a positive sign for this. And as spontaneous emission will make the N2 decay, and also this one the stimulated emission will make the N2 to decay, we have taken these two terms with negative sign. But at equilibrium, this rate of change of N2 would be equals to 0. So if you set this thing equal to 0, and if you try to write down the expression of rho from this equation, we get this, where we have pulled out B21 into N2 as a common factor. So we have gotten this one. So if you express this thing slightly different way, that means if you write A divided by B21, and if you cancel out N2 and N2, we get this expression for rho. As per the Boltzmann's statistics, the ratio of N1 and N2 should be exponential minus E1 minus E2 divided by KT, where K is the Boltzmann's constants and T is the temperature of the black body. So if you write this exponential with positive sign, it should be E2 minus E1 by kt. But if you consider that E2 minus E1 is equals to h cut omega, where omega is the frequency of the light that will be emitted during spontaneous emission, or maybe during stimulated emission, then we can write this thing as h cut omega, I mean n1 by n2 as e power h cut omega by kt. And if you substitute this into the expression of rho, we can get this like this. But as per Planck's distribution of spectral energy density of a black body, this rho as a function of omega should be equal to this quantity. So if you actually kind of compare the expressions for rho from the treatment of light and from the black body derivation, then you will see that a by b21 should be equal to this quantity, and then b12 divided by b21 should be equal to 1. So these are the relationships which are called Einstein, the relationships among Einstein coefficients. That's it in this video, and thanks for watching.